Okay, good morning everyone. My name is Changshuo Zhang. I'm from Renmin University of China, and my supervisor is Professor Xiao Zhang and Professor Jun Xu. And today I'm thrilled to share our latest research named Reinforcing Long-Term Performance in Recommender Systems with User-Oriented Exploration Policy. First of all, I will give the background and the challenges. Recommender systems are the backbone of many digital services, from e-commerce to social media. In recent years, there have been a notable surge in the interest in reinforcement learning-based recommendation, given its distinctive ability to explore the interests and elevate long-term performance within the recommendation. And in contrast to the traditional supervised methods that optimize immediate user feedback, RL-based recommendation it treats the streaming recommendation problem as an interactive process, and it's focusing on maximizing the cumulative rewards of users in the long term. The challenges in applying RL to recommendation are multifaceted. Intricate user behavior patterns may make exploration more difficult. And second, the users of different activity levels require different level of exploration. And to better illustrate the challenge, we conduct experiments with the content-based grouping of users on a public short video dataset named Querent. And specifically, we arrange users by their total number of clicks. Subsequently, we select users from various bottom quantiles that from 0 to alpha, like the 20%, 40%, 60, 80, and 100%. And of this sorted outcome, and this represents the users of the bottom alpha of the activity levels. And we then evaluate the performance of the two typical RL methods, the DDPG and TD3, and we evaluate the two methods under different level of noise on these user groups, such as the 0.010, 0.05, 0.1, 0.5, and the larger noise represents the larger exploration intensity, and the figure demonstrates that as the quality decreases, indicating users with lower activity level, there is a tendency for them to exhibit the performance for higher noise intensity. And the observation suggests that the optimal exploration intensity varies across different user groups, and emphasizing the importance of the implementing more effective and fine-grained exploration in RL-based recommendation. Okay, based on the above observation, we will begin the introduction of the formulation and the method. And this is the formulation of our approach, UOEP, and we focus on the session-based recommendation, where the goal is to select the items for the user at each time step, aiming to maximize the cumulative rewards over the sessions. And we model this as the Markov decision process with the following components. And the first S is represents the state space, including both static features such as gender and age, and dynamic features such as the historical interactions. And A is the action space, which includes all possible recommendation lists within a session. And R is the reward function, mapping user state and action to an immediate reward. And it reflects the user feedback such as clicks or likes. And the policy function, the pi, denotes the probability of selecting action with a given state S. And the standard RL objective is to maximize the expectation of the return distribution. But in our objective, we replace the expectation with a distortion operator, the D. And here we chose the CVR, so named the conditional value at risk, which captures the expected return when experiencing a given bottom, the alpha quantile of the possible return distribution. And the quantile function denoted as the F inverse. And it is the inverse function of the cumulative distribution function of the return distribution Z pi. And it maps a quantile value tau from 0 to 1 to the corresponding value within the distribution. And specifically, when alpha equals to 1 and the CVER value is equal to the expectation of the entire distribution. And at the basis of our approach is the distributional critic, powered by the implicit Contel network, IQN, and this network allows to approximate the Contel function F inverse. And we calculated the temporal difference, the TD error, which is crucial for the critic optimization. And to accurately learn the relations between contels, we utilize the tau contel Huber loss defined as this, and the critics loss is defined as follows for all levels by sampling n independent contels and n independent target contels. And this is the heart of our approach, is the population of vectors, as shown at this, the population of vectors. And we assign unique alpha values to each of the actor and to focus on different contels of the return distribution. And we contain the CVR for each of the actor with the critics output Z theta. And we use a Monte Carlo sampling method to approximate it. And the loss function is defined as the below. And otherwise, we introduce a mechanism to address the blindness to success problem. That is, we continuously decrement the alpha value from 1 to the given alpha value during the training process. Okay, and then to maintain the diversity and stability in our actor population, and we employ the behavior embeddings and the kernel metrics within our loss function. The behavior embedding donated as the phi pied serves as a vector representation of an actor's action. And this is implementation by the sampled state S sampled from the replay buffer and sent into each of the actor and output the actions. And this representation is embedded within the behavior space, facilitating the measurement of a similarity between different actors. And to compare each two different actors, we employ a kernel function K to map their behavior embeddings to a high-dimensional feature space, and which our choice is the squared exponential kernel. And then we compute the kernel matrix, the K, among the actors within the population, defined as this. And geometrically, the determinant of this metric, delta K, is corresponding to the volume of the parallel pipette defined by the feature mappings of the chosen kernel function. And a larger volume indicates a high degree of diversity within the population. And we optimize the diversity within the actor population, and we optimize the diversity as a regularization term in the population loss function, and this function is defined as this below. And this ensures that each actor explores this distinct action spaces, enriching the overall recommendation strategy. And then we introduce a supervised loss, a binary cross entropy loss for the training stability. And the overall population loss is defined as the equation below. It is componented by the each actor's loss and the stability loss and the diversity loss. Okay, and here is the algorithm implementation, and we train an online environment simulator. And then we choose the DDPG algorithm as the backbone of our approach, UEP algorithm. And on the left is our training procedure of our method. And from line 2 to the line 5, each actor roll out in the environment, and that is to interact with our trained simulator. And from line 7 to line 10, and we perform gradient descent. And then we have conducted extensive experiments on 3 public recommendation datasets, and the Query, the movie lens, and the RL4RS. And the baseline is the supervised learning, the A2C, DDPG, DD3, and some Workpetinger and the JC, which encourage exploration. And metrics is total reward, is the total reward within a session, and depth. Depth is the interaction times within a session. And the results are promising, showing our approach outperforming other baselines in the long-term performance. Okay, to understand the working mechanism of our approach, we plot the t-SNE embedding of the 5 actors learned by our population for generating actions. And during the test phase, we random sample a subset of users and serve them with the 5 learned actors. And the generative actions are displayed in different colors in this figure. And from this distinct clusters for each actor. And this clustering action demonstrates that our method effectively explores a broad action space customized for different users. And throughout the ablation studies, we have examined the effect of different components of our approach. And first, we disable the distributional critic in UOEP and replace it with a deterministic critic. And in other words, it's all our actors optimize the expectation of the cumulative return distribution. And then we learned the ablation of the two regularization loss, the diversity loss, and the stability loss. And finally, we found that both are essential for the algorithm success. Okay, another point is that our UOP strategy of dividing user into groups based on the bottom alpha values. And the alpha value in our implementation is setting as the 0.2, 0.4, 0.6, 0.8, and 1. And resulting in overlap among these groups. For instance, the group of 0.4, it includes the users in the 0.2 group. And this overlap in grouping is cited by two fundamental reasons. And the first is to focus on the low activity users. The low activity users stand to gain more from the high intensity exploration, and it helps explore their latent interests. And the second is to mitigate the overestimation of Q values, which is a common issue in the RL-based recommendation. And the tendency is to overestimate the value of actions. And in the figure, we implement without overlap version at the red line, and the original version, the green line. It shows that we sampled some states and actions and calculate the Q value. It shows that it's an overestimation of the without overlap version. And then we conduct main experiments and show some performance. Okay, and finally, our UEP also shows great potential in improving the experience for low activity users and ensuring fairness. And the metrics are CVR 0.3 means that a bottom 30% of the return distribution, and the Gini metrics for the fairness. And by focusing on the tail end of the return distribution, and we can better serve users who are often overlooked by the traditional recommender systems. Okay, thank you for your attention, and this is my email and the code I released, and this is our IRS lab link, and this is my WeChat. I'm now open to any questions you may have about my research. Thank you.